The MIPS are 10K, 10,000. Superscalar is microprocessor. Out of order, Superscalar microprocessor executes instructions beyond those installed by the cache misses. This minimizes the time lost due to the latency by completing the upper instructions and other instructions and initiating the subsequent cache refill early. The MIPS R10000 is a dynamic and superscalar microprocessor that implements the 64-bit MIPS 4-instruction set architecture. The it fetches and decodes 4 instructions per cycle and dynamically issues them to 5 fully pipelined low-latency execution units. The instructions can be fetched and executed speculatively beyond the branches. The instructions graduate in order to open its completion, and although the execution is out of order, the process still provides a sequential memory consistency and precise exceptional handling. The R10000 is designed for a high performance even in large real-world applications with poor memory locality. With speculative execution, it calculates the memory address and initiates cache refills early. Each hierarchical, non-blocking memory system helps hide memory latency with 2 levels of associative and write-back caches. Figure 1 shows the R10000 system configuration, and the R10000 box lists its principal features. Out-of-order superscalar processors are inherently complex. To cope with this complexity, and R10000 uses a modular design that locates much of the control logic within the regular structure, and they introduced including the activity list and register map tables and instruction queues. Designed rationally, the memory bandwidth and latency limit the performance of many programs. Because packaging in a system costs to constrain these resources, the processor must use them efficiently. The R10000 implements register mapping and non-blocking cache, which complete to each other to overlap the cache refill operations. Thus, if an instruction misses in the cache, this hardware immediately adapt whenever cache misses delay instructions, so the processor looks at up to 32 instructions to find a possible parallelism. The instruction window is large enough to hide most of the latency for refills that the secondary cache. However, it can hide only a fraction of main memory latency, which is typically much longer. It is relatively easy to add non-blocking caches to an out-of-order processor because it already contains mechanisms that coordinate dependencies between instructions. Implementation. We implemented the initial R10000 microprocessor using 0.35 micrometer CMOS technology on a 16.64 times 17.934 millimeter chip. This 298 millimeter square millimeter chip contains 6.8 million transistors, including 4.4 million in its primary cache arrays. We implemented data paths and time-critical control logic in full custom design, making wide use of the dynamic and latch-based logic. We synthesized the last critical circuits using the static register-based logic. So the MIPS R10000. This processor features a 4-way of superscalar RISC processor that fetches and decodes 4 instructions per cycle. The speculative execute beyond the branches with a 4-entry branch stack. It uses dynamic out-of-order execution. They implement register renaming using map tables and achieved in order graduation for precise exceptions. 5 independent pipeline execution units include a non-blocking load store unit and their 64-bit integer ALUs, 64-bit IEEE standard 754, 1985 floating point units, and a pipeline adder with 2-cycle latency and a pipeline multiplier with a 2-cycle latency. So the hierarchical non-blocking memory subsystem includes on-chip 2-way associative primary caches, 32 kilobyte instruction cache, and 32 kilobyte 2-way interleaved data cache, an extended 2-way associative secondary cache, and a 128-bit wide synchronous static RAM, and a 64-bit microprocessor system interface with the split transaction protocol. System flexibility. Alternate configuration allow the R10000 to operate in a wide range of systems as a uniprocessor or in a multiprocessor cluster. The system maintains cache coherency using either Snoopy or the directly based protocols. So the R10000's secondary cache ranges from 512 kilobytes to 16 megabytes. The operation overview. Figure 2, next page, shows a block diagram and pipeline timing diagram for R10000. There are 6 nearly independent pipelines, so the instruction fetch pipeline occupies stage 1 through 3. In stage 1, the R10000 fetches and lines next to 4 instructions. In stage 2, it decodes and renames these instructions and also calculates target addresses for jump and branch instructions. In stage 3, it writes the named instruction into queues and reads the bit enable table to determine if the operands are initially busy. Instructions wait to queues until all their operands are ready. So the 5 execution pipelines begin when a queue issues an instruction in stage 3. The process reads operand from the register files during the second half of stage 3, and quotient execution begins at stage 4. So the integer pipeline occupied 1 stage, and the load pipeline occupied 2, and the floating point pipeline occupied 3. So the processor writes result into register file during the first half of the next stage. The Figure 1 system configuration. The cluster bus directly connects as many as 4 chips. The integer and the floating point sections have separate instruction queues, register files, and data paths. This separation reduces the maximum wire lengths and allows fully parallel operation. Together, 2 register files need more free registers than would a combined unit, but they are physically smaller because each register has fewer read or write ports. So instruction fetch. For good performance, the processor must fetch and decode the instructions at a higher bandwidth that it can execute them. So it's important to keep their queues full so they can look ahead to find instructions to issue out of order. Ultimately, the processor fetches more instructions than it graduates because it discards instructions occurring after mispredicted branches. So the processor fetches the instruction during stage 1, as shown in figure 3. So the instruction cache contains address tag and data sections. To implement a 2-way set associativity, each section has 2 parallel arrays. The processor compares 2 tag addresses to translated physical addresses to select data from the correct way. The small 8-entry instruction translation lookup buffer TLB contains a subset of a translation in the main TLB. So the processor fetches the 4 instructions in parallel at any word aligned within the 16-word instruction cache line. We implemented this feature with a simple modification to the cache sense amplifiers, as shown in figure 4. Each sense amplifier is wired as 4-bit columns in the memory array, and a 4-to-1 the multiplexer selects one column which represents one instruction for fetching. The R10000 fetches a line instruction using a separate selected signal for each instruction. These instructions rotate if necessary so that they are encoded in order. The ordering reduces the amount of time-dependent logic. So this is figure 2 is the R10000 block diagram and a pipeline timing diagram, and the block diagram shows the pipeline stage left to right the corresponding pipeline time in. So usually the processor decodes all 4 instructions during the next cycle unless the queues or active list is full. Instructions that are not immediately decoded remain in the 8-word instruction buffer, simplifying the timing for sequential fetching. Branch unit. Branch instructions occur frequently and must execute quickly. However, the processor cannot usually determine the branch direction until several or even many cycles after the decoding the branch. Thus, the processor predicts the directions a conditional branch will take and fetches instructions speculative along the predicted path. The prediction uses a 2-bit algorithm based on a 5 and 12 entry branch history table. This table is indexed by bit 11 to 3 of the address of the branch instruction. Simulations showed an 87% prediction accuracy for spec 92 integer programs. In the MIPS architecture, the processor executes the instruction immediately following a jump or a branch before executing instructions at the target address. In a pipeline scalar processor, this delay slow instructions can be executed for free while the target instruction is read from the cache and for free while the target instruction is read from. This technique improves the branch efficiency in early RISC-V processors for processors. So for a superscalar design, however, it has no performance advantage, but we retained the feature in the R10000 for compatibility. When the program executes, take, adjust, or branch, the processor discarded any instructions already fetched beyond the delay slot. It loads the jump's target address into program counter and fetches new instruction from the cache after one cycle delay. These introduce a branch bubble cycle, so during which 10,000 decodes no instructions. The branch stack. When it decodes a branch, the processor saves each state in 4-entry branch stack. This contains alternative branch address, the complete copies of integer and floating point map tables, and miscellaneous control bits. Although the stack operates as a single logical entity, it is physically distributed near the information it copies. So when a branch stack is full, the processor continues decoding only until it encounters the next branch instructions. So decoding banner stores until the resolution of one of the pending branches. The branch verification. The processor verified each branch prediction as soon as each condition is determined, even if the earlier branches are still pending. If the prediction was incorrect, the processor immediately also aborts the old instructions fetch along with the mispredicted path and restores each state from the branch stack. Fetching along these mispredicted paths may initiate unneeded cache refills. In this case, the instruction cache is non-blocking and the processor fetches the correct path while these refills complete. It's easier and often desired to complete such refills since the program execution may soon take the other direction of the branch, such as the end of a loop. The 4-bit branch mask corresponding to entries within the branch stack that accompanies each instruction through the queue and execution pipeline. This mask indicates which pending branches the instruction depends on. If any of these branches was mispredicted, the processor will abort the instruction when the branch decision is reversed. Whenever the R10000 verified a branch, it resets the corresponding mask bits throughout the pipeline. Decode logic. The R10000 decodes and maps the 4 instructions in parallel during page 2 and writes them into the appropriate instruction queue at the beginning of the stage 3. Decoding the loop. Decoding stop if the active list or a queue becomes full, but there are very few decode restrictions that depend on the type of instructions being decoded. The principal exception involves the integer multiply and divide instructions, and their result to go into special registers, high and low. No other instructions have more than one result register. We did not add much logic for these infrequently used instructions. Instead, they occupy 2 slots in active list. Once the processor decodes such an instruction, it does not decode any subsequent instruction during the same cycle. In addition, it cannot decode an integer multiply or divide as the 4th instruction in a cycle. Instructions that read or modify a certain control registers executed serially, the processor can only execute these instructions, which are mostly restricted to rare cases in the kernel operating system mode when a pipeline is empty. This restriction has little effect on overall performance. Register mapping. Figure 5 illustrates the R10000 register mapping hardware. To execute instructions out of their original program order, the processor must keep track of the dependencies on register operand, so the memory address and condition bits. The condition bits are 8 bits and a status register set by floating point compare instructions. To determine the register dependencies, the R10000 uses register renaming. It determines the memory address dependencies in the address queue. It sets each condition bit operand during the code if its value is known. If not, it renames the bit with the tag of the floating point compare instructions that will be eventually set its value. From a programmer's perspective, instructions execute sequentially in order the program specified. When an instruction loads a new value into its destination register, that new value is immediately available for subsequent instructions to use. However, a Superscalar processor performs several instructions simultaneously, and their results are not immediately available for subsequent instructions. Frequently, the next sequential instruction must wait for its operand to become valid. The operand of later instructions may already be available. The R10000 achieves a higher performance by executing these later instructions out of order, but this reordering is invisible to the programmer. Any result is generated out of the order is temporary until the all previous instruction has completed. Then this instruction graduates and its result is committed as a processor's state. Until it graduating, an instruction can be aborted if it is followed the inception of a restricted branch. The previous contents of its logical destination register can be retrieved by restoring its previous mapping. In most processors, there is no distinction between the logical register number. There is a distinction between the logic register numbers, which are referenced within the instruction field, and physical registers, which are located in the hardware register file. Each instruction field directly addresses the corresponding register. So our renaming strategy, however, dynamically maps the logical register's number into physical register number. The processor writes each new region into a new physical register. So after mapping, the process determines the dependencies simply by comparing the physical register numbers. It's no longer must consider instruction order. Again, the existence of these physical registers and the mapping of the logical registers to physical registers are invisible to the programmers. The R10000 executes instructions dynamically after resolving all dependencies in the previous instructions. That is, each instruction must wait until all its operands have been computed. Then the R10000 can execute that instructions regardless of the original instruction sequence to execute the instructions correctly. The processors must determine when each operand register is ready. This can be complicated because the logical register's numbers may be ambiguous terms of operand values. For example, if several instructions specify the same logical register simultaneously in the pipeline, that register may load repeatedly with different values. There must be more physical than the logical registers because the physical registers contain both committed values and temporary results for instructions that have completed but not yet graduated. A logical registers may have a sequence of values as instructions flow through the pipeline. Whenever an instruction modifies a register, the processor assigns a new physical register to logical destination registers and stores these assignments in register in map tables. As the R10000 decodes each instruction, it replaces each of the logical register filled with the corresponding physical register number. Each physical register is written exactly once after cache assignment from the free list. Until it is written, it is busy. If subsequent instruction needs each value, and the instruction must wait until it is written. After the register is written, it is ready, and each value does not change. When a subsequent instruction changes corresponding logical register, then the result is written into a new physical register. When this subsequent instruction graduates, the program no longer needs the old value, and the old physical register becomes free for reuse. Thus, physical registers always have unambiguous values. There are 33 logical, number 1 through number 31, and high and low, and 54 physical integer registers. There is no integer register 0. A 0 operand field indicates 0 values. A 0 destination field indicates an unstored result. There are 32 logical numbers 0 through 31 and 64 physical floating point registers. Bitmap tables. The separate registers files store integer and floating point registers, which the processor renames independently. The integer and the floating point map tables contain the current assignment of logical to the physical registers. The processor selects logical registers using 5-bit instruction field. 6-bit addresses in the corresponding registers file identify the physical registers. The floating point table maps register F0 through F31 in a 32x times 6-bit multi-port RAM. The integer table maps registers R1 through R31 high and low in a 33 6-bit multi-port RAM. There are special access logic for high and low registers. The implicit destination of integer multiply and divide instructions. These map tables have 16 read ports and 4 write ports, which map 4 instructions in parallel. Each instruction needs the mapping for 3 operand registers and 1 destination register. The processor writes the current operand mapping and new destination mapping into instruction queues. So while the active list saves the previous destination mapping, so the R10000 uses the 24 5-bit comparators to detect the dependence among the 4 instructions decoded in parallel. These comparators control bypass multiplexer, which replaces independent operand and a new assignment from the free list. Next, the free list. The integer and floating point free list contains a list of currently unassigned physical registers because the processor decodes and grades 8 up to 4 instructions parallel. This list consists of 4 parallel 8-bit and circular FIFOs. The active list. The active list records all instructions currently active within the processor. Depending on which instructions the processor decodes it, the list removes the instructions when they graduate, or if a mispredicted branch or inception causes them to abort. Since after 32-bit instructions can be activated, the activated list consists of 4 parallel 8-bit circular FIFOs. Each instruction is identified a 5-bit tag, which equals an address in active list. When an execution unit completed the instruction, it sends its tag to the active list, which sets its dump bit. The active list contains logical destination register numbers and each old physical register number for each instruction. On instruction graduated commit its new mapping, so the old physical register can return to the free list of reuse. When an exception occurs, however, subsequent instructions never graduate. Instead, the processor restores an old mappings from the active list. The R10000 maps 4 instructions per cycle in reverse order, in case it named the same logical registers twice. Although this is slower than the restoring a branch, and exceptions are much rarer than a mispredicted branches. The processor returns a new physical register to the free list by restoring their read pointers. BG bit tables. For each physical register instead of floating point, BG bit tables contain a bit indicating whether the register currently contains a valid value. Each table is a 16 for 1-bit multi-room RAM. The tables set a bit busy when the corresponding register leaves the free list. It resets the bit when an execution unit writes a value into this register. 12 read ports determine the status of the 3 operand registers for each of the 4 newly decoded instructions. The queues use 3 other ports of a special case instruction, such as moves between the integer and floating point register files. Instruction queues. The R10000 puts its decode instructions, except jumps and no operation nodes, into one of the 3 instructions queues according to type. Provided there is room, the queue cannot accept any combination of new instructions. The chip cycle time constrains our design of the queues. For instance, we dedicated 2 register file read ports and on each issued instruction to avoid delays, arbitrating, and multiplexing operand buses. The integer queue. The integer queue contains 16 entries in no specific order and allocates an entry to each integer instruction as it is decoded. The queue releases the entry as soon as each issued and the instruction 2 on ALU. Instructions that only one of the ALU can execute have the priority for the ALU. Thus, the branch and shift instructions have a priority for ALU1. The integer multiply and divide have a priority. So for ALU2, for simplicity, location of the queue less than instructions, AG determines priority for issues. However, a round robin recast circuit raises the priority of the old instructions requesting ALU2. The figure 6, integer instruction queue showing only one issue port. The queue issues the instruction in parallel. So figure 6 shows the contents of integer queue entry. It contains 3 operand selector fields, which contain physically registered numbers, and each contains a ready bit initialized from the busy bit table. The queue compares each select with the 3 destination select corresponding to the right port integer register file. Any compare error matches set the corresponding ready bit when all operands are ready, and the queue can issue the instruction to on execution unit. Operand C contains either a condition, bit value, or a tag or a floating point. Compare the instruction that will set its value. In total, each of the 16 entries contains 16 comparators, and the queue issues the function code and immediate values to the execution unit. The branch mask determines if the instruction aborted because of a previous predicted branch. The tag set down in the active and active list after the procedure complete the instruction. The single instruction latency of an integer instruction complicated integer queue timing logic. In one cycle, the queue must issue 2 instructions, detect which operands become ready, and request depending on instructions. Figure 7a illustrates this process. To achieve 2-cycle load latency, an instruction that depends on the result of the integer load must be issued tentatively, assuming that the load will be completed successfully, so the dependent instruction is issued to 1 cycle before it is executed. While the load reads and the data cache after load fails because of cache miss or dependency, the issue of the dependent instructions must be aborted, so the figure 7b illustrated this process. The address queue. The address queue contains 16 entries. Unlike the other two queue, it is a circular FIFO that serves the original program order that is instructions. It allows an entry when the processor decodes each load or store instruction and removes the entry after the instruction graduates. The queue uses instruction order to determine the memory dependencies and to give priority to the oldest instruction. So when a processor restores a mispredicted branch, the address queue removes all instructions decoded after the branch from the end of the queue by restoring the right pointer. The queue issues the instructions to the address calculation unit using the logic similar to that used in integer queue, except that this logic contains only 2 registers operand. So the address queue is more complex than the other queues. A load or a store instruction may need to be retried if it has a memory address dependence or a misses in the data cache. The 16-bit and 16-bit by 16-bit matrices, the track dependencies between the memory accesses The rows and columns correspond to the queue's entry. The first metric, avoid unnecessary cache trashing by tracking which entries access the same cache set. Virtual address 1350 for 13.5. Either way in a set can be used by instructions that are executed out of order. But if the two or more queue entries address different lines in the same cache set, the other way is reserved for oldest entry to access the set. The second metric tracks instructions that load the same bytes as a pending store instruction. It determined this match by comparing double word address and 8-bit byte masks. Whenever its external interface accessed the data cache, the processor compared its index to all pending entries in the queue. If a load entry matches the refill address, it passes the refill data directly into destination register. If an entry matches an invalidated command, that entry state clears. All the address queue execute load and store instructions out of their original order. It maintains the sequential memory consistency. The external interface could violate this consistency, however, by invalidating the cache line after it was used to load the register, but before that, let's load the instruction graduate. In this case, the queue creates a soft exception on the load instruction. This exception flushes the pipeline and aborts the load and all later instructions, so the processor does not use the stale data. Then, instead of continuing with the execution, the processor simply resume normal execution, beginning with the aborted load instruction. This strategy guarantees forward progress because the oldest instruction graduated immediately after completion. The store instructions require special coordinate between the address queue and active list. The queue must write into a data cache precisely, and the store instruction graduates. The MIPS architecture simulated atomic memory operation with the load link LL and the store conditional as the instructions pairs. So, the pairs. These instructions do not complicate system design because they do not need to lock access to memory. In a typical sequence, processor loads a value with an error instruction, tests and modifies it, and then conditionally stores it with an SC instruction. The SC instruction writes into memory only if there was no conflict for the values and a linked word remains in the cache. The processor loads each result register with 1 or 0 to indicate if memory was written. The floating point queue. The floating point queue contains 16 entries, as very similar to the integer queue, but it does not contain the immediate values. Because of extra wiring delay, the floating point needs to have the 3-cycle latency. So figure 8 ALU1 block diagram. Register files, integer and floating point register files, each contain 16 physical registers. Execution units read operands directly from the register files and write the result directly back. A result may bypass the register file and to open the registers, but there are no separate structures such as reservation stations or reorder buffers and a wide data path. The insert register file has been read ports and 3 write ports. These include 2 dedicated read ports and 1 dedicated write port for each ALU and 2 dedicated read ports for address calculator unit. The integer registers 7th read port handle store and jump register and move the floating point instruction. The 3rd write port handles load, branch and link, and move from the floating point instructions. A separate 64-word times 1-bit condition file indicates if the value in corresponding physical register is 0. The 3 write ports operate in parallel with the integer register file. Each 2 read ports allow integer and floating point conditional move instructions to test a single condition bit instead of entire register. This file used much less area than 2 additional read ports in the register file. The floating point register file has 5 read and 3 write ports, and the adder and multiplier each have 2 dedicated read ports and one dedicated write port. The 5th read port handles store and move instructions. The 3rd write port handles load and move instructions. The integer execution unit. During each cycle, the integer queue can issue 2 instructions to the integer execution unit, integer ALUs. Each of 2 integer ALUs contains a 64-bit adder and a logic unit. In addition to the ALU1 contains a 64-shift branch condition logic, and ALU contains a partial integer multiplier area and integer divider logic. The figure 8 shows the ALU1 block diagram. Each ALU has a 60-volt operand register that are loaded from the register file. To achieve the 1 cycle latency, the 3 ports of the register file bypass into the operand register. The integer queue controlled both ALUs. It provided a function called immediate values and bypass the control and so forth. The integer multiplication and division. ALU2 iteratively computes the integer multiplication and division. As mentioned earlier, this instruction has 2 destination registers, high and low, for multiply instructions. High and low contain the high and low halves of a double precision product. For divide instructions, they contain the remainder and quotient. So ALU2 compute integer multiplication using both algorithms, which generate a partial product for each 2 bits of the multiplier. The algorithm generates and accumulates 4 partial products per cycle. ALU2 is for the first cycle after instruction is issued, and the last 2 cycles to store the result. To compute an integer division, ALU2 uses a non-restoring algorithm that generates 1 bit per cycle. ALU2 is for the entire operation. Table 1. List the latency and repeat the rate for common integer instruction. Floating point execution unit. Figure 9. Show the mantissa data path for these units. Exponent logic is not shown. The adder and multiplier have 3-stage pipelines. Both units are fully pipelined with a single cycle repeat rate. The result cannot bypass the register file for either 2 cycle or 3 cycle latency. All floating point operations are issued from a floating point queue. Floating point values are packed in IEEE standard 754 single or double precision formats in the floating point register file. The execution unit and all internal bypassing use an impactive format and explicitly store the hidden bit and separated 11-bit exponent and 53-bit mantissa. Operands are unpacked, they are read, and results are packed before they are written back. Packing and unpacking are implemented with 2 input multiplexers that are select bits according to the single or double precision format. This logic is between the execution unit and register. The floating pointer adder. The adder does floating point addition, subtract, compare, and conversion operations. Each first two stages subtract the operand component and select the language of operand and align the smaller mantissa in 55-bit right shifter. The second stage adds or subtract the mantissas depending on the operation and size of operand. A magnitude addition can produce a carry that requires 1 bit shift right for post-normalization. Conceptually, the processor must round the result after generating it to avoid the extra delay. A dual carry chain adder and generate both +1 and +2 versions of the sum. The processor selects the +2 chain if the operation requires a right shift for post-normalization. On the other hand, a magnitude subtractor can cause massive cancellation, producing a high order zeros in the result. A leading zero prediction circuit determines how many high order zeros per subtraction will produce. Each output controls the 55-bit left shifter that normalizes the result. The floating point multiplier. The multiplier does floating point multiplication in a full double precision array. Because it is slightly less busy than the ladder, it also contains a multiplexer that performs move and conditional move operations. During the first cycle, the unit booth encodes the 53-bit mantissa of the multiplier and use it to select 27 partial products. With booth encoding, only one partial product is needed for each 2 bits of the multiplier. The comprehension tree uses an array of 4 to 2 carry save adders, which sum 4 bits into 2 sum, and carry output during the second cycle, result in 1 and 6-bit sum, and carry values are combined using a 1 and 6-bit carry private adder. A final 53 bits adder around the result. Floating point divider scale root. The independent iterative using compute floating point division and scale root operation. Each unit uses SRT algorithms that generate 2 bits per iteration stage. The divide unit cascades 2 stages within each cycle to generate 4 bits per cycle. These units share the register 5 ports with the multiplier. Each operation preempts 2 cycles. The first cycle issues the instruction and reads its operand from the register file. At the end of operation, the unit uses the second cycle to write the result into register file. Register to list the latency and repeat the rate for common floating point instructions. Memory hierarchy. The memory hierarchy, memory latency, has a major impact on a processor performance. To run large programs effectively, an R10000 implements a non-blocking memory hierarchy with 2 levels of set associative caches. So the one core, one chip, primary instructions and data caches operate concurrently, providing a low latency and a high bandwidth. The chip also controls a large external secondary cache. All caches use a least recently used LRU replacement algorithm. Both primary caches use a virtual address, index, and a physical address tag. To minimize latency, the processor can access each primary concurrently with the address translation in TLB in each TLB. Because each cache way contains 16 gigabytes, 4 times than the virtual page size, 2 of the virtual index bits, 13 to 12, might not equal bits in a physical address tag. This technique simplifies the cache design. It works well as long as the program uses consist virtual index to reference the same page. The processor stores the 2 virtual address bits as part of the secondary cache tag. The secondary cache controller detect any violations and ensure that the primary caches retain only a single copy of each cache line. The load store unit, figure 10, contains a block diagram of the store unit and a data cache. The address queue issues load and store instructions to address calculation, unit and data cache. When caches are busy, a load instruction simultaneously accesses the TLB, catch date tag array, and a cache data array. These parallel access result in two-cycle load latency. Address calculation. R10000 calculates virtual memory addresses of the sum of the two 64-bit registers or the sum of the registers and the 16-bit immediate field. Result from the ALUs and the data cache can bypass the register files into the operand registers. The TLB translates its virtual addresses to physical addresses. And memory address translation, TLB, the MIPS for architecture to find a 64-bit addressing. So practical implementation to reduce the maximum address width to reduce cost of the TLB and cache tag arrays. The R10000 fully associative translation leukocyte buffer translates 44-bit virtual addresses into a 40-bit physical addresses. This TLB is smaller than that of the R4000, but we increased it to 64 entries. Each entry maps a pair of virtual pages and independently selects a page size of any power of 4 between the 4 kilobytes and 16 megabytes. The TLB consists of content addressable memory, CAM section, which compare virtual addresses, and RAM section, which contains corresponding physical addresses. Primary instruction cache. The 32 kilobyte instruction cache contains 8,192 instruction words, each pre-encoded into a 36-bit format. The process can decode this standard format more rapidly than the original instruction format. In particular, 4 extra bits indicate which functional unit should execute the instruction. The precoding also rearrange operand and destination select fields to be in the same position for every instruction. Finally, it modified several opcodes to simplify decoding of the integer of floating point destination registers. So the processor simultaneously fetched 4 instructions in parallel from both cache away, and the cache logic selected the desired instructions. These instructions need not be aligned on a quad address, but they cannot cross the 16 kilobytes words cache line. See figure 3. The primary data cache. The data cache interleaves two 16 kilobyte banks for increased bandwidth. The processor will allocate the tag and the data arrays of each bank independently for the following requesting pipelines. 1. External interface. Refill data, intervention, and so on. Tag check and follow newly calculated address and retrying a load instruction and graduating a store instruction. To simplify interface and reduce of the amount of buffering required, the external interface has priority for arrays needs. It requests occur two files, both for cache read or write. On the processor, they can have a reducing error. The data cache has an 8-word line size, which is a convenient compromise. Larger size reduce the tag RAM array area and modestly reduce this mislead, but increase the bandwidth consumed during refill. With an 8-word line size, the secondary cache wide size upon 3 hour 3 4 3 or 4 left refill. Each of the data caches, two banks comprises two logical arrays to support two-way set associativity, unlike the usual arrangement. However, the cache ways alternate between these arrays to efficiently support different width access as each of the data caches, two banks, comprise two logical arrays to support the two-way associative, unlike an unusual arrangement. However, the cache way alternative between these arrays to efficiently support different width accesses as figure 11 shows. So, the processor simultaneously reads the same double word from both cache ways because it checks the cache tags in parallel and later select the data from the correct way. It discards the double word from the incorrect way, so the external interface refill or writes quad words by accessing two double words in a parallel. This is possible because it knows the correct cache way in advance. The arrangement makes efficient use of the cache sense amplifier, which amplifier includes a 4-to-1 multiplexer anyway, because there are 4 columns of memory cells for each amplifier. We implemented this feature by changing the select logic. The secondary cache, we used the external asynchronous static RAM chips to implement the 512 kilobyte to 16 megabyte two-way set associative secondary cache. Depending on a system requirement, the user can configure the second cache line size at either 16 or 32 words. Set associativity reduces conflict misses and increases the predictability for an external cache. However, this usually requires special RAMs to many more interface pins. Instead of R10000, implement a two-way pseudo-set associative secondary cache using standard synchronous RAMs and only one extra address pin. Figure 12 shows how cache refills are pipelined. The single group of the RAMs contains both caches. An on-chip bit array keeps track of which words was most recently used for each cache set. After a primary means, two quad words are read from this way, and the secondary cache. Each tag is read along with the first quad word. The tag of the alternate way is read with the second quad word by a toggling of the extra address pin. The trick occurs if the first way hits, data becomes available immediately. If the alternate way hits, the processor reads the secondary cache again. If neither way hits, the processor must refill the second cache from memory. Large external caches require error correction code for data integrity. The R10000 stores both 9-bit ECC code and a parity bit with each data quad word. The extra parity bit reduces latency because it can check quickly and stop the use of bad data. If the processor selects a correctability error, it retries leading through a 2-cycle correction pipeline. We can configure the interface to use the correction pipeline for leads. Although this increases latency, It allows redundant lockstep processors remain synchronized in a presence of correctable error. 2. The system interface. The R10000 communicated with the outside world using 64-bit split transaction system bus multiplexed letters and the data. This data can directly connect as many as 4 R10000 chips in a cluster and overlaps up to 8 requests. The system interface is dedicated to substantial resources to support concurrently out-of-order operation, cache refills and unblocking with up to 4 outstanding read requests from either the secondary cache or the main memory. These are controlled by the MIPS handling tables. The cached buffer contains addresses for four outstanding read requests. The memory data returned from these requests is stored in the 4-entry incoming buffer so that it can be accepted at any rate and in any order. The outgoing buffer holds up to 5 victims blocks to be written back to the memory. The buffer required the 5th entry when the bus evaluated the secondary cache line. An 8 entries cluster buffer tracks the standing operations on the system bus. The ensured cache coherency by interrogating and, if necessary, by invalidating cache lines. So the uncached loads and stores execute serially when they are oldest instructions in the pipeline. The processor often uses uncached stores for writing to graphics or other preferred devices. Such sequences typically consist of numerous sequentially or identically addressed to access. The uncached buffer automatically gathers those into 32-bit word blocks to conserve the bus bandwidth. Clocks. An on-chip phase clocked loop PLL generates all timing synchronously with an external system interface clock. For system design and upgrade flexibility, independent clock divider give users the choice of 5 secondary cache and 7 system interface clock frequencies. To allow more choices, we based these clocks on a PLL clock oscillating at twice the pipeline clock. When the pipeline operates at 200 MHz and the PLL operates at 400 MHz, and the user can configure the system interfaces to run at 300, 133, and 180, and 66.7 and 56 or 50 MHz. In addition, the user can separately configure the secondary cache to frequencies between 200 and 66.7 MHz. So up drivers. For groups of the buffers, drive chips often pins. The user can configure each group separately to conform to either low voltage CMOS or HSTL standard. The buffer designed for each group has special characteristics. Figure 13, next pages, illustrate how these buffers connect and the system interface. Buffer contains additional open drain pull-down transistors, which provide the extra current needed to drive HSTL class 2 multi-drop buses. We designed the secondary cache data buffer to reduce overlap current spike and switching, because nearly 200 of these signals can switch simultaneously. The cache address buffer uses large totem pole transistor to rapid drive multiple distributed loads. So the cache clock buffer drive low impedance differential signals with minimum output delay. A low jitter delay element precisely around these clocks. This delay is statistically configured to adjust for propagation delays in a printed circuit board clock net. So the clock lives at the cache simultaneously with the process internal clock. The test features. For the economical manufacturer, a microprocessor chip must be easy to test with a high fault coverage, So the R10000 observes the internal signals with 10 128-bit linear feedback shift registers. This internal test point partition into the chip and 3 fully observed sections. The registers are separate structures that do not affect the processor's logic or logic noticeable load to observe the signals. They use the processor's clock to ensure the synchronous behavior and avoid any special clock requirements. They are useful for debugging or testing. So, performance. We are currently shipping 200 MHz R10000 microprocessors in Silicon Graphics Challenge servers, and several vendors will soon ship the R10000 in systems specifically designed to use its features. We project that such a system with a 200 MHz R10000 microprocessor, 4 MB secondary cache, 200 MHz, and a 100 MHz system interface bus, and 180 nanometer a nanosecond memory latency will have the following performance. Spec 95 Intel's peak 9. Spec 95 FP. Peak 19. We schedule this benchmark result from the performance of an R10000 running on an actual system in which processor, cache, and memory speeds were proportionately slower. We compiled the benchmarks using early version of the MIPS Mongoose compiler. Acknowledgement. R10000 was designed by the MIPS T5 project team, whose dedicated made the claim a reality. The figures in this article is derived from author's design notes and are used with permission from MIPS Technology Incorporation. Okay, today I read this paper, the MIPS R10000 Superscalar Microprocessor. Thank you for your time. See you next time.